Here you see a hello world in Jai programming language, and naturally if I run it, so compile, you can see Jai path to the file and execute it immediately. Naturally there is some compiler output and at the end hello sailor. Here it is. At the top of the program you see import basic, where basic is the name of the module. Basic contains a set of useful utilities such as print, and you see import. Import is a directive. Directives are things that start with a hash. And print accepts a string and prints it to the console. So far so good. And by the way, if you hear this name Jai for the first time, this is a systems programming language developed by Jonathan Blow, a very famous game developer who created Braid, Witness, and also upcoming game Order of the Sinking Star that is scheduled to come out somewhere in 2026 as of time when I am recording this video. And that game, Order of the Sinking Star, is written in this new programming language. The language itself is in closed beta and it is scheduled to get into public beta somewhere after the game is released. And I've been in this beta for over 2 years at this point, and for the last 5 or so months I've been using this language full time. And of course we wouldn't be here if I just wanted to show you a hello world. But before we get into some more interesting stuff about this language, we need to warm up a little bit, okay? For example, here's how you declare a variable. You put a name of the variable as the first thing, then you put a colon, after which you put a type, for example S64, 64-bit signed integer. Then you put an equal sign and you give it a value, for example 6. And after that you can pass a % sign, which is a placeholder for whatever you put here in the print, and then you can recompile and rerun the file, and here it is, hello sailor 6. As you can see, unlike in C, you don't need to provide any type signifiers like %s. Jai just knows that it is an integer and it can print it just like that. And another way you declare something is a constant. So for example, if you declare b, you can make it unsigned 64-bit integer, and then instead of an equal sign, you give it another colon. Now b is a constant. And so again, if we just rerun the program, it reruns normally, we didn't pass b anywhere. But if you try to reassign, which is just plain equals without any colons, for example 27, and rerun the file, you will get a compile error, attempt to assign to a constant. So you can see how you have a place for the type and place for the value that can be either variable or a constant. And on top of that, Jai has a type inference, which means you don't need to always provide types. It can actually just infer the types if you leave the slot empty. So let's make, for example, b a string. So this is a string. Here you can see that we just don't have a type here, and the language will just happily eat it. And for example, if we pass another % sign here and provide b here, again, no type formatters here, and we run the program, you can see hello sailor 6, and this is a string, just like that. Now we are arriving to a very interesting observation. You might notice that this b : is suspiciously similar to main : and this is actually not a coincidence. As it turns out, procedures, which is how Jai calls functions, follow the same exact rule for the definition. And so, for example, if we try to pass something to main, for example, a as a string, you can see that entry point must have no arguments. Here it has 1. And what does it mean? It means that main is actually a procedure that takes no arguments. And also it returns no values. So we can literally provide a type here in the type slot. And if we recompile the program, we can see it runs no problem. But of course, this is kind of redundant. So while you can do this, you don't actually need to do this. And also, as a matter of fact, you can make procedures non-constant by assigning main. And yes, it works as well. So you can see how this variable and constant declaration is consistent no matter at which level it is used. And even more so, so let's get it back to constant, modules follow the same exact rule. So you can assign basic to a constant named basic, just like that, through a double colon. And if you recompile now, you can see that print is undeclared because you forcibly namespaced the module. And now to access print, you need to access it through a basic namespace. And now you can see it works again. Now, you might be thinking, okay, so you have assigned this thing to constants and variables, and A and B you pass to a print function. Does it mean you can pass main procedure to a print as well? And the answer, of course, you can. So if you do this and recompile, there you have it. This is a string and then procedure and the address of a procedure. Yes, you can pass procedures to functions, you can assign them to variables. Jai, unlike some other systems programming languages, has functions or procedures as first-class citizens. And actually not just procedures, really any type. So if you want to declare a struct, so for example, this is how you declare a struct in Jai, you can just take this foo straight up and pass it into a print as a type. And if you recompile, you can see the print just prints foo. And so we are not getting confused. You can do an f of a type foo. So you can see that I put foo in the type slot without defining a value itself. And I also pass an f here instead of a b. You can see here that 6 and then an empty struct because foo doesn't have any fields. And then foo itself here as a type. And so it is even clearer. Let me do another print where I guess like type of f is something and type of foo capital F is something else. And let me just do type of f and type of foo. And we run this program and now we can see that type of f is foo, our struct, and type of foo is capital T type. You can see where I'm leading to. Jai has types as first-class citizens and it has higher order types. And it's not just about structs. So for example, if we pass a type of A, which is gonna be S64, we can also pass int here just as a plain variable. And if we recompile this program, we can see that type of A is S64. And it prints int as S64 because int is actually just an alias. But if we do type of int, now we get the capital T type as well. This actually gets even more interesting because Jai has quite a unique type that almost no other programming language has. And this type is capital C code. Right, so if I print, and if I print this A, you can see that A is of type code. And how do you even declare something of a type code? Well, you use a directive code. Again, directives are things with hash at the start. And code can be, well, any code. So for example, b equals 2. And if you recompile, you can see it compiles. But how do you use this code? Again, let me remove the capital C code. So we have a type inference and let me make it into a constant. One of the things you can do with code in Jai is you can insert it into a program. So for example, I can type insert, which is another directive A. And now, yes, now you can see I've inserted the code and this code gets type checked. We see a compile error here, undeclared identifier B, because I am trying to assign B and I need to actually properly declare it. And now it works. And so since B is inserted, I can actually print it like this. And we can see that it prints 2. This is not the only way you can insert the code. You can also have it as a string literal. So for example, A can be just a string and then you can insert this string literal with the insert directive. And if you recompile it, You can see something interesting. Error, we parsed a declaration, so we expected a semicolon after it. So Jai takes this string literal, it parses it as a code, and it tries to type check it before it inserts into a program, but in this case it can't even parse it because the code needs a semicolon at the end. And now if we recompile it, we get b equals 2, so you can see no code directive here. And you probably think now about all sorts of crazy things you can do with it, because as I've shown previously, you can just pass the code. Yeah, let's make it a code again, so it's not just a string. You can just pass code chunks into functions. And now if you ever saw a Lisp programming language, you pretty sure find this familiar, right? You can pass code as data, and we all know what Lisp is capable of, right? A big difference between Jai and Lisp though is that Jai is strongly typed and statically compiled language. So after inserting this chunk of code, you can't just assign something else to b. b is a 64-bit integer, so if I run it, it will say type mismatch, type wanted as 64, type given string, which makes this whole machinery way more maintainable, which will come up later in the video. And the last thing I wanted to point out before we switch to actually fun stuff is that Jai has a compile time execution. So let's go back to our regular hello sailor, there you have it, and run it as normal. So here it is, hello sailor. So if you want to run some code at compile time and Jai lets you run absolutely any code at compile time, all you need to do is put run directive in front of it. And you can see that at the moment we have hello sailor after all of the compiler output. But if I rerun our program again, you will see hello sailor before even linker runs. And as a matter of fact, we can print hello, let's do it runtime sailor, and this is comp time sailor. And you will see that comp time sailor runs before the linker, and then runtime sailor runs when we run our compiled program. And this opens another can of infinite possibilities of what you can do in the language. And now the real fun begins. So let's imagine you have some kind of a user that you store somewhere in a database, which will be in a struct, and it will have a name which is a string, and maybe age, which is unsigned integer, and something, I don't know, like notifications, which is some pointer to notifications to some kind of other struct that we can also define. It's gonna be plural, I think that's better, right? So it's gonna be another struct, and it's gonna have some settings for important notifications and maybe marketing, something like that, right? All of the stuff is somewhere in the relational database, and you want to fetch it with select, but before that you want to build a query, and sometimes you don't want to return all the fields. And usually in systems programming languages you would do some lame stuff like return the entire structs, but some fields are nulls or maybe just zeroed out. But with Jai we can have some fun. So let's define a build query procedure that will return, well, since we have first class types, it will return a type, and it will also accept a type, which is a type, and it will accept fields that we want to return, so fields, yes, which is probably gonna be something like array of strings. So let's start at that. You can see a $sign between fields. $sign just means that this is a constant. It can be in front of the type, it can be in front of the value itself. And this is how generics also work in Jai. For the purpose of this video, just know that if you have something in the procedure arguments that has a $, in front of it, it means that this is a constant. Of course, we don't have a type user with name defined anywhere. And if we run the program, we see this error. Declaration claims to be constant, but uses an expression that is not constant. And this is because we return some kind of a type from build query that we don't know at compile time. And the thing with Jai is it is a statically compiled, strongly typed language, which means that types of everything needs to be known at compile time. So Because of that, we need to invoke this procedure at compile time, and we do it by prefixing it with run. And now, if we run it again, we have another error. So this procedure did not return any values while generating a polymorph. It will create a different version of build query with every type we call it here, with every type and every field. So let's implement this. No matter what we do, we will gonna return this output type. And since this is not some type we predefined, like for example user or notifications, we will have to insert it into our target program with insert directive. And insert does not just accept code and string literals. It can also insert return of a compile time execution, so it builds on top of run. And you don't even need to specify run directive here. There's a little syntactic sugar that you just say that this is gonna return string and open a code block, so a pair of braces. And yes, I said string because you can also return code here. And so, for example, something like return code blah blah blah, right? So you can do this, but at the moment code in Jai doesn't have a lot of syntactical sugar built on top of it. So for example, if you know Lisp, then you know that in Lisp you can quote something and then inside you can like unquote stuff and you can replace parts of the code with something else. Jai doesn't have this syntax quality of life on top of code now, so we will build code dynamically out of string chunks, and we'll see how it goes, what instruments Jai provides us to make it maintainable and debuggable. So one thing that Jai provides in its basic module is a string builder. So let's start using it. And string builder is what you expect. You can push string chunks onto, and at the end you concatenate them into a single string. And by the way, in Jai strings are sized, so a string is actually a struct with a count and a pointer to a data. So any normal modern programming language has strings like that. And so we're gonna open a block here, and after we are done, we are going to have our result type is going to be something like builder to string with a string builder passed by pointer. And so all the chunks that we have with string builder will be concatenated into a single string that will get returned to us. And at the end, we will gonna just return this result type. So what's gonna be in here? Well, first let's do some validation on the input parameters. Since we accept a type here, we don't really know what type the user will provide. And we really only want to work with structs because that's where we select our fields from. And so Jai has a runtime and compile time type reflection, which is powered by type info structs. And we can get it by calling a built-in type info procedure that we provide a type into. And this type info has a type on it. So we, for example, can check if info.type is a struct, just like this, and we can assert on it. And if it's not, we can provide an error, build query only supports structs. Something like this, right? And if we compile, we have an error because there is no output type, which makes sense. So maybe let's just stop things so we can test our validation out. So yeah, let's actually just return user for now with all the fields, and now it compiles, and let's call build query again, but now we call it with an integer, which is not a struct. And if we recompile, we can see a compile time error, assertion failed, build query only supports structs. And if we click on the error, we go straight here on our assertion. And yes, I want to point out that this is in fact a compile time error, not a runtime error, because this code inside of insert is running at compile time. All right, so we start by printing to our builder. There is append that we provide a pointer to string builder, and our struct that we insert, let's call it output type. You can dynamically generate output types, and you can even then get the type by name at compile time. I'm not gonna bother with it just for the sake of simplicity and not to overload with too much information. We're gonna do it a simple way. After which we make it into a struct. We're gonna open a brace and add a new line symbol. And then we need to iterate over these fields, cross-check it against the user fields and pick those that are matching, and probably return a compile error if some fields are unexpected. And the way you do it, well, you iterate by fields like this, and you can assign this to a variable, so field, so for field in fields, kind of like this. And then field is going to be every one of this array. Let's open an internal for loop, so for member of info.members. So yeah, type info of the struct has each member's type info on it, and maybe actually it's going to be helpful if I just open the definition of type info struct, so let's just do it. So there it is. It is in preload module that ships with Jai. So here is type info struct. You can see we have a name of the struct. So if we wanted, we could use it here. It has parameters because structs are can be also polymorphic in Jai. We're not gonna cover that, but here it has members. So each member of the struct is each of these fields, and it is a type info struct member. And if we go, we can see that each type info struct member has type. Here it has its own type info, it has its name, it has offsets in bytes in the struct, and a bunch of constants. So what we're gonna check here is we're going to check if member name equals to field, and then we're gonna process it here. But I guess we also need to find out if something is in there. So let's just declare a variable found here. And at the end of this loop, I guess if not found, we're just gonna assert. Actually, let's not assert. Let me show something else. Let's do compiler report. So this is another way to report compile time error. And we're gonna use a print. So this is like string print. It's kind of like sprintf in C. And we provide it an error message like field % does not exist on, I don't know, like on the struct, and we pass it a field and then struct name. And do we have a struct name? We don't have a struct name. So the way you get struct name is, of course, on type info struct, you get a name. So struct name equals info.name. Also, compiler report, if we open its definition, here it is in compiler module, we can see that it accepts something called lock, which is caller location by default. So let's not provide anything here. Let's just compile and see. While executing this run, we stalled waiting for another directive. So what this error means, it means that I screwed something up here. And since we run this at compile time, this run thinks that maybe, oh, something is missing, and it will get inserted from some other part of compile time execution, and so it waits for us. So let's put stallable on it for now. You don't need to know what it means. It just kind of means if there is an error, show it us right away. And naturally, undeclared identifier compiler report, because as I said compiler report is in compiler module, so we need to import it as well. Like that, and if we recompile, there you go. What it says, field name does not exist on user. Well, it's because I haven't set found to true here, right? And if we recompile again, there we go. While building string returned by this insert directive, it doesn't find a closing bracket. So yeah, let's actually do it right away. And Jai has a defer keyword. Defer means just run whatever is here at the end of the scope. It's kind of like in Go, but more powerful, because in Go it only works on the procedure, but in Jai it works on scope basis. So let's print to builder. So actually there is print to builder, and there is also append. Append just appends a string chunk. Prints to builder accepts formatting. I'm not using formatting here, I just wanted to show you the difference. And so at the end, we just insert this. So end of line and like that. Okay. Of course, semicolon, and if we run, error name is not a member of type info integer, because here we pass an int. So instead, let's pass something that does not exist on the user. For example, I don't know, just foo. And if we run it, look at this. Compile time error. Field foo does not exist on the user. And if we click, we go right here on the compiler report, which is actually probably not the best location, because imagine if you do this in a real code base, you probably want this error to point you here. So you can see, oh yeah, foo indeed doesn't exist on the user. You probably are not concerned as much of the implementation details. And so this is where you can pass a location, custom location here for the compiler report that you can actually get here. So loc equals in Jai procedures accept default parameters, and caller location is another directive that gets you a source code location of whoever called us. So in this case, it's going to be this file and this line. So if we compile again, we can see that attempt use variable from, what's that? Oh yeah, because location must be constant. So this is another interesting point. If you want to use a variable in a compile time block, naturally it must be constant, right? Because you can't use runtime variable at compile time. So if we recompile it, field foo does not exist on the user, and if you click on the error, it brings you at the call site. So it's very convenient for the user. I know it was a bit fast, but let's take a pause and process it. I just showed you that you can customize compiler errors so that when you do something complicated at compile time, you do some crazy metaprogramming, you can always provide users with sane compile errors and point them to the correct location that will help them to debug it. This makes this whole situation way more maintainable in practice. But yes, let's continue. So after we found our target field, we need to print it to builder. So print to builder. And we pass our string builder here, and let's indent it nicely. And then how does it look? So it looks like a name of the field, then its type, and then a semicolon, and then end of the line. So let's just literally do this. Percent, semicolon, percent, so percent colon, percent semicolon, end of line. And we pass it a member.name, because remember, so here type info struct member, name, and type is its type info. So member.name, and then we can't pass just type info because type info is this struct. We actually need the name of the type, or I guess the type itself that represents this type info. And you can get type from type info by calling get type and pass it a member.type. So that's literally it. And get type only works at compile time. So as of now, the language doesn't allow you to get type from type info dynamically at runtime. After that, we break here, I guess. And is this it? I mean, maybe this is just it. So let's see if field foo doesn't exist. Let's kill that. Let's compile. And it actually compiles. So let's check it out. Supposedly, we have this type created for us at compile time. And so now we should be able to assign a variable to this type. So user with name, right? And let's say we got the value from somewhere. So name equals Bob. And then let's print it, right? So let's print u, just like that. And if we print, we get Bob 0 and null because I forgot to return the type. So I insert this in the code and I need to return output type, of course. Now if I compile, yeah, I get just Bob. So just let's think for a second. I created a type programmatically at compile time based on an existing type. Just like that in 15-20 lines of code. And if I try to set a name that doesn't exist on it but exists on the user, so age equals, I don't know, 69. Bob is 69 years old. And I try to execute the program. Here, age is not a member of output type. And another important thing here is that here is the definition of output type. And it brings us to a file called added strings somewhere. And if I click on it, look at this. We have our string that we built at compile time nicely printed out here. And it says us that inserted text generated from main.jai at line 17. So it's literally where we inserted it here. even if you do some crazy string templating here, at the end of the day, Jai will take whatever you generated, it will put it into a file, and it will plug it into compile time machinery that will give you nice errors with a pointer where it all leads, just so you can sanely debug it. And actually, if it's some runtime code, so not just type, it can be any code, arbitrary code, if you run your program through GDB, you will literally break into this code with a breakpoint. So it's super maintainable actually. It's very easy to debug what you did here, and it helps a lot. And to continue, for example, so if we put H here and we recompile, now we see that Bob has H and the name. Maybe let's do another one, users with notifications, and let's do notifications here. Again, like this, let's create U2 with user with notifications, and let's just, I don't know, print it. And we get an error, field notifications does not exist on user because there's a typo here. Yeah, and now it should work. There you go. Oh, I accidentally undid too much. Here we have, so Bob and null. And null here because we have a pointer to a struct, so we can maybe create notifications here, and Jai by default zeroes out the memory of the struct. So if we do U2 notifications equals to pointer to n, and then print U2.notifications, and of course we need to dereference it. This is how you dereference a pointer in Jai. You can see false, false. So just like that, we created a couple new types based on an existing type at compile time, and at the same time it's fully type safe. So all of this code that we generated here got parsed by the compiler, got type checked, and only then inserted after the compiler knows it's sane. And then you know that you are safe at runtime because you can't use fields that you didn't fetch from the database. Okay, but if you want to get not all of the notifications, maybe you want just some subfields. And I'm not gonna go and implement this, but the situation is exactly the same. So you can imagine two different scenarios here. You can maybe come up with some DSLs, like you can put a colon here and maybe important, right? Or maybe important marketing, something like that. And here you can get a member name, you can split it by colon, then you can enter a recursive loop, split it by comma, and do exactly the same situation. You can insert the notification subtype, then you can insert that subtype on this type, and it's gonna work in exactly the same way. But in my opinion, creating a DSLs like that is kind of weird. I never liked DSLs that relies on string literals too much. So the way I would do it, and again, I'm not going to implement it, I'm just going to show you the API that Jai supports. Additionally to an array of strings, have an array of subtypes. And subtypes can be an array of subtype. And what is a subtype? Subtype can be another struct that can have a name and then, guess what? A type, which is a capital T type. And you can kind of see what I'm leading to. Again, this must be constant. And for example, if you want only some field of notifications, you can, instead of passing a field of names, you can pass an array of these subtypes. So again, I'm calling a dot here because I can type a subtype, but since Jai knows that this expects array of subtypes, I can omit this and rely on type inference. And let's say I only want important here, important bool, just like this, and this should be a field name, so notifications. And then this is gonna be a struct that is again like here. So this is another syntax that Jai supports. Again, this is a subtype struct. So maybe let's type it out fully. And the first field is the name. So this name, again, this must be a struct. I can do it like this. So name equals this, and then type equals this. And you can see that I just pass a struct like that. And it is because Jai supports anonymous structs. So you can define a type in Jai without giving it a name. So just like at the very start of the video, we found out that this syntax is universal and this is just the thing that you assign to the name. You can also have it just as a value that you can also pass around. And you can use this as a nice way to declare subtypes of an existing type. And again, not enough arguments. Yes, because now this doesn't provide anything. And since Jai supports default values, I can just say that, okay, default array of subtypes is empty. And now type mismatch, type wanted string, type given subtype. It's because it actually expects an array of string first. So array of fields is going to be empty. And now we get an error that notifications are not there because we didn't provide anything here. So notifications. Again, you see compiler caught us. We tried to use notifications on the type that we created that doesn't have it. And now, yeah, we're back to compiling state. And again, I'm not gonna handle this code, but you can see how it can work. We got an array of subtypes. You can iterate over each one of them. You can get a type info of this struct. You can iterate over each field of this struct and compare name against these fields and build the subtypes recursively and then assemble it all together. And all of that in barely a 30 lines of code. And it's not just some C macro craziness. At the end, the compiler provides you with the result string that you can actually look into and cross-check and even break in with debugger. This is just so beautiful. But wait, there's more. At the moment, we looked at code directive that you can pass a code literals around, and we've seen at assembling code from string literals. But there is actually another super low level way to create code. And we kind of got a glimpse of it by importing compiler module. But if we go back into a compiler module here, so this is a compiler module from Jai distribution, and we go somewhere up, we can see a bunch of interesting structs that start with code. And for example, let's see at code struct maybe. So here it is. So code struct is a subtype of code node. So as using base doesn't matter. It just basically means that there is a base struct which we are a subtype of. And if we go to code node, look at this. Code node is a simple struct that only has a pointer to a type info, its location in the file, some serial number, and which kind of it. And it is an enum with a lot of values, and you can see block, literal, identifier, unary operator, binary operator, blah blah blah, while, if, case. So this is an AST of Jai, literally syntax of Jai, abstract syntax tree exposed to you as a user through a set of structs and utilities that you can use to create the code straight from these tree primitives and then at the end insert it. So this gives you super low level control over the AST. And if you use it directly, it's gonna be super verbose because it's super low level. So usually the way you use it is by receiving messages from the compiler during the compilation and do some targeted changes where you need it, or maybe save code chunks into array and then process it in a way. But you can totally just raw dog it. In fact, I do this in one of my projects, and I even built like a higher level library to help me with using this all machinery. And now I'm gonna show you just how a lowest possible level of this code looks like if we would implement this same functionality with it. But I'm not gonna type it all from scratch because it's quite a bit of code. I actually pre-typed it. So let me just paste it and boom. And it was 30 lines of code and now it's 80 lines of code. So quite a bit of a difference here, but just let's look at it real quick. And of course, if we compile and run it, it works just as before. So we have our Bob here that only has a name, and we have our guy with notifications here. And if we try to do something silly like assigning an age to a Bob, we get a compile error. Age is not a member of output type. Yeah, and one nuance here is that here is the definition of output type. Since we don't assemble this from a string anymore, we actually just decided to go straight to the caller location right here. So you see the error will bring us here instead of to the declaration of the output type. Yeah, because there is no string formatted here. It's just all from AST. Other than this minor detail, the code works exactly the same. It's actually a little bit more powerful. Let's take a look at it. It starts relatively normally. We get our type info the same way we did from the incoming struct, but then we start creating AST trees. So first of all, we create a struct node, which is code struct, which is this thing. And then we need to assign this struct to the name. So we need to create a declaration, which is created here. And the name of our declaration is output type. And new is just a lightweight helper to allocate stuff on the heap. I'm not even bothering clearing anything, so freeing, because this runs at compile time. And when compiler exits, all of the memory that we don't need will get freed, and none of this will go to runtime, right? Because compiler is just kind of fire and forget. And so inside of the struct, we need a block. So opening brace and closing brace. So inside of this, we have a block, and block consists of statements. So each internal declaration is a statement. And as I said, each statement is a declaration. So here's our array of statements. And yeah, our declaration is constant because again, colon, colon. And we also assign a location to our struct code. So we set line number, character number from this location. And file is gonna set by default. It just knows which file it's in. So far, it's kind of makes sense, right? We just literally following the language syntax tree rules. Next, we iterate over array of fields the same way we did before. We also have our little found flag. We also iterate over every type info member, so member of the struct. And for each struct, we need to create a statement that is a declaration. So here we create another declaration. And if we go and look at the source code of the declaration here, each declaration has an entry of the scope that has its name, and also it has type instantiation and expression. And there is a helpful comment. So type instantiation, let me do it like this. Type instantiation is A, so here it's the type, and expression is B, so this thing. And we need to create a type instantiation. So here we're creating it. So we have name, string, notifications, a pointer. So on the field declaration of the name that comes from this entry, we put the member name, and type instantiation, we create it anew. After that, we need to create an identifier. So because this string in the terms of abstract syntax tree, it's identifier, it's not a type. Type is more of a high level construct, right? Here we are working with the code. So we need to create an identifier string, identifier U32, identifier notifications. Okay? Yeah, so here it is. We create a code identifier. And if we go here and find a code ident, here it is, code ident just has a name of the string, and it also has a result declaration that we don't need to set. If we assign this ident to a statement and statement to a declaration, compiler will figure it out for us. But yes, so here's our identifier. Then we assigned member.type, so the type info of a member from the type info struct. So I hope you're still following, but in our case, it is the thing from preload. So it will be this type info on a type info struct member. And then we need to handle a case where it is a pointer. So when we assigned the type from the string, we didn't care about it. We just took the string and added it to another string. But here we actually need to care. So in our case, notifications is a pointer. And in abstract syntax tree, if you go to type instantiation declaration, it has a field pointer to, and it is a recursive, right? So code type instantiation can be a pointer to another code type instantiation. So here we are looping while the type is a pointer. We get it a type info pointer from it. We create nested type instantiation. So this one, we assign it to a field pointer 2 of our outer type instantiation. We reassign this to nested, and we reassign member type. So this is like a recursive loop. We just go as deep as pointer 2 is, and we just restore this chain in our syntax tree. And at the end, finally, we can add the name. So we also call getType just like in our previous implementation, and we put it as a name of identifier. So hopefully you see what's going on. We created abstract syntax tree as deep as we need in case of pointers. And then at the end of the chain, we put the name of the type, which in our case would be notifications, capital N, right? And so this thing supports whatever depth we want. It's just gonna chain it all together in this while loop. After that, we put type valued expression to this identifier. So this thing is gonna be identifier of string, so this one. And after that, we add this newly created declaration, right? Name, string, age, U32. We add it to array of statements. And at the end, after we're done with the whole loop, we put this array of statements as statements of our block, so the inside of these curly braces. And then our outer declaration is a code node. To take code node and turn it into a code, we need to call compiler get code. And this output code, this is some debug output, we don't need that. We just return. And note that our insert now returns code, not string. And fair enough, when we execute it, we get our functionality back. So you can see how this machinery gets you super low level control of every little minutia of the compiler syntax tree. And by the way, this is a casting syntax. So you just take member type, that is a pointer to type info, and you downcast it to type info pointer like that. There you go. This is an example of super low level compile time metaprogram. This is as low of a level as you can go. I just wanted to demonstrate it to see the flexibility you have if you so desire. And there we have it, a little demonstration of just the tip of the iceberg of what Jai offers you in terms of compile time execution and metaprogramming. There is so much more things I didn't cover here. I just wanted to kind of showcase why I like this language a lot. I'm a big fan of metaprogramming. And also, if you notice, the compile times are pretty much instant. It shows you here a little stats, and on my computer, it cranks about 1 to 150k lines of code a second. So yeah, I enjoy this language a lot. As I said, I've been programming in it full time for the past like 5 months, and also I've been in a closed beta for over 2 years at this point. I literally can't wait for this language to come out in public so we can all share joy of programming in it together. And thank you for watching. If you want more Jai, feel free to let me know. And yes, see you in the next video. Bye bye.